Hello and welcome, ladies and gentlemen, to another episode of Mr. Smith Talks About Calculus. Coming at you live from beautiful San Juan Capistrano, California. Kind of broke my own rule, and I'm working during Thanksgiving break, so that's why we're recording from home today. Today we're going to be tackling section 3.8 from Louis Leitholt's The Calculus 7, so titled Summary of Sketching Graphs of Functions. So this is really kind of the capstone to the first 7 sections of chapter 3 minus 3.2, where we're going to be using critical points of our first derivative, our second derivative, looking at our asymptotes, both vertical and horizontal, and coming up with some sketches of graphs with calculus as kind of our guiding principle on this stuff, where in previous math courses we've kind of been guessing on a lot of this stuff. Well, now calculus allows us to kind of laser in and come up with some pretty accurate sketches of our graphs. This should be hopefully a pretty quick video. We're just going to go through one example, just kind of lay out everything that you're going to be looking for and trying to show, and then set you loose on some problems. A lot of this is just going to be a review, so hopefully it goes pretty smoothly. So if you want to take out your notebooks, change over to my document camera. Working. Oh, working. Okay, let's slide this bad boy over. On page 276 in your textbooks, you've got summary of sketching graphs of functions. And you've got this like 11 item list. We're not going to write this down because I assume you can read. But we will walk through an example where we check every single one of these things off the list as we go. And yeah, let's get to it. You're all staying happy and healthy during this Thanksgiving break. Go. What do we got? We got pens and pencils, straight edges, lines and tigers and bears. Oh my. Here we go. 3.8. Summary of sketching graphs of functions. Oh, it's going to be real fun. Real fun. Okay, and we'll kind of use this green box on page 276 as sort of our roadmap, or so to speak. And so, again, we're going to just do one example. Example 1. And the function we are going to consider is called f. And it is so defined as x squared plus 3 diviso a x minus 1. Cool. Cool. So we want to come up with a sketch of what this function's curve is going to look like, what its graph will look like. And there's a lot of questions that come with trying to sketch a function. Like, what numbers can we plug into this thing? Usually the first question, otherwise known as, what's the domain? Like, is there any no-fly zones here? And so question or item 1 on that list is determine the domain of f. Well, it's So it's not a polynomial, it's a rational function, so we can't just say all reals, but it's pretty close. We can see there's a trouble spot at 1. Other than that, seems like we can plug anything in here and we're going to be okay. So our domain, introduce some set notation here. We're going to say x in the set of real numbers. X is in our real numbers, so long as or such that x is not equal to 1. Okay, so this just means all real numbers except for 1 is our domain. Cool. Okay, so once you figure out the domain, you're like, all right, so I can plug in everything but 1, which we'll come back to that in a quick second. That probably means something about an asymptote, but we'll return to that. Usually the next thing we look for, or kind of progression of our understanding of graphs throughout our math careers, has been, okay, domain, how about intercepts? Because that's usually, those are some kind of keystone points, is where does this thing cross our two axes, our horizontal and vertical axes? So starting with the x-axis, we'll call this intercepts. So we're just organizing this as best we can. Number 2 on that list is find x and y intercepts. It does note that when finding the x-intercepts, you may need to approximate the roots of the equation f of x equals 0 on your calculator. We'll come to that if we need to. So let's consider our x-intercepts. Okay. Where does this function cross the x-axis? Well, it's going to be when f of x equals 0. Is this ever going to be equal to 0? Because in order for this to be equal to 0, our numerator would have to be 0, but x squared plus 3, anything we plug in for x is going to be positive, and you add something to a positive number, that ain't never going to be 0 in our real number system. And yeah, so it's got imaginary solutions, but imaginary solutions don't cross our x-axis. So there are no x-intercepts. Kind of the rationalization we can say here is that x squared plus 3 is going to be greater than 0 for all x. Never going to be equal to 0. Okay. Well, what about our vertical axis? Is there any points where it's going to cross the y-axis? And our hunch is yes, because the vertical asymptote that we're kind of hinted at is x equals 1. So we think that it will cross that y-axis. But in order to do that, we're going to plug in 0 for our x's and see what happens. So our y-intercept can be found by inserting a 0 for our x's. Zero squared is 0, plus 3 is 3. 0 minus 1 is negative 1. So our y-intercept is at negative 3. Cool. So it doesn't cross the x-axis, but it's going to cross at negative 3. All right. And I guess we can make that into a point. 0, negative 3. Got our first point. Woo-hoo! But 1 point does not a graph make. We're going to try and do better than that. Okay, so we've got our domain, got our intercepts. Next question is usually, or what you will ask yourself next, is there any symmetry going on here? And the book in this example kind of just flies by it and says, oh, there is no symmetry with respect to either the y-axis or the origin. A note about that, I'm only going to really think that we should test for y-axis symmetry. We could do the origin, or I guess maybe we should do the origin. Well, we'll start with the y-axis and then we'll make a call. So symmetry. But if you read through this example, you'd be like, oh, there's no symmetry, cool, but they don't say why or how. So symmetry can be tested by, for the y-axis, basically figuring out, is this an even function? Okay? Does every x, y correspond to a negative x, y? If you plug in a negative x, you get the same thing. And the way we can test that is taking our function rule, plugging in a negative x, and if it spits out the same thing, then you've got symmetry about the y-axis. So we're going to test f of negative x, because again, if that spits out the same function on the right side, that means that anytime you plug in a negative x, you get the same y value as when you plug in a positive x. And you can picture that, it's like, it's down here, like positive x gives you some point, you plug in that negative x value, gives you the same point, you'd have that symmetry. Okay, like the parabola is the perfect example of that. So we'll plug that in. Negative x squared plus 3. That's looking good. Down here, though, we have a negative x minus 1, and then feels less good now. The top, certainly, we square this negative x, and we get x squared plus 3. On the bottom, though, negative x minus 1 is not the same as x minus 1, and so there is no symmetry about the y-axis. Some of you might be thinking, well, shouldn't we test symmetry about the x-axis? Yeah, except if we have symmetry about the x-axis, we'll be in a function. Okay, we're not going to worry about x-axis symmetry. So what this means is no y-axis symmetry. Do we want to do about the origin? I'm trying to think if we're going to give you any that have origin symmetry. Let me check the back of the book. Because I did this before I started recording, but then that would make too much sense. It might be. Yeah, there's one. Yeah, so the way that we're going to test for origin symmetry is think about the origin, and it's like when it folds down on itself. So if you're symmetric about the origin, it means that when you have an xy point, you also have negative x, negative y. Okay, it's kind of like this across the origin. So the way we test that is we plug in a negative x, and if it spits out the opposite of this thing, then we do have that symmetry about the origin. So well, I guess we already did that. So if we pull out, so we did that, and if we pull out that negative there from the bottom, we get x plus 1 over x squared plus 3. And I know this sort of feels like it's giving us the opposite of this, but in order to have the opposite of this, we would need a negative x squared minus 3 on top with x minus 1 on the bottom, or we would need a negative x plus 1 on the bottom. Okay, which again, I know it looks like it's close to that, but it's not. Okay, it's not quite the opposite of f of x here. Okay, so no symmetry about the origin. That's how we would test that. That is a very kind of obscure case. The y symmetry is kind of the more common. Okay, so that's 1, 2, and 3. Number 4 says, check for any possible horizontal, vertical, or oblique asymptotes. Cool. And in order to do that, you will have needed to watch 3.7, which talks about those horizontal asymptotes or limits at infinity. So hopefully you've done that. If not, press pause and go do that now. So the asymptotes. Asymptotes. Probably one of the funnest words in the English language to spell. Or another way to think about asymptotes is our end behavior. Kind of synonymous. Vertical. Kind of already talked about that. Vertical is going to be that hole in our domain. Can't plug in 1 for x. You have vertical asymptote there. So x equals 1. Horizontal. We're going to test. So horizontal just means what are we doing as x gets really big, and what are we doing as x gets really small? Is it approaching some value? So horizontal limits at infinity. So the limit of f of x as x increases without bound. So this is a limit at infinity. It's going to be the limit as x increases without bound. Remember the trick that we use here when we have this rational function is we're going to find the largest power of x and divide everything by that and then make our life easier. So we just try to sub here. We're going to get infinity squared plus 3 over infinity minus 1. And it's like, I don't know what that is. So we need to do some trickeration there. And the trickeration is just take x squared plus 3 and x minus 1 and divide them both by x squared, which will result in 1 plus 3 over x squared divided by 1 over x minus 1 over x squared. Okay, cool. Now when we do these limits, we can do them separately. And we had that theorem that told us that when we have 1 over x raised to some power, or really 1 over, to any rational, or any, I think rational might just work. And we'll call it any integer power. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The limit of 1 over that thing as x increases without bound is 0. So that's going to be 0, that's going to be 0, that's going to be 0. This turns into 1 plus 0 over 0 minus 0. So the top becomes 1. And then there is a bit of a tricky moment here. Okay, 0 minus 0. Well, it's probably 0, right? Yeah, but the question is what kind of 0? Is it approaching 0 from positive or negative values? And so I don't know if I made enough of a point about this in 3.7, so I will do so now. What we need to figure out is 1 over x minus 1 over x squared. Is that difference going to be positive or negative? Obviously, it's going to trend towards 0 because eventually these things just become super, super small. But is 1 over x super, super smaller, or is 1 over x squared super, super smaller? Well, let's use some like intermediate values. If x is 100, 1 over 100 is 1 over x. 1 over 100 squared is like 1,000, 10,000. I can math, I promise. This guy is smaller than this guy. And so as we subtract these will be it'll be a positive shrinking value because 1 over x is always bigger. So this is going to be a positive 0, which means that we are increasing without bound as x increases without bound, which means there is no horizontal asymptote in that direction. It just gets big. Okay. In the other direction, as x decreases without bound, we're going to use the same conception of f of x to test this. Well, the limit as x decreases without bound of 1 plus 3 over x squared divided by 1 over x minus 1 over x squared. Same thing happens up here. We get 1 plus 0. And we got to be a little bit careful here. Same sort of tricky moment here where we're going to have 0 over, or 0 minus 0, but we need to question what type of 0 is this approaching. And it's tempting just to use the same logic as here. Say, oh, well, it's going to be bigger, that's going to be smaller, it's going to be positive. But this is decreasing without bound. These x values that are going in there are negative. So for our 1 over x squared, it behaves the same. However, 1 over x is going to be negative values, okay? Really small negative values, but negative values nonetheless, okay? And so this infinitesimally small negative number minus another infinitesimally small positive number is going to result in a negative 0, okay? And you could go down a rabbit hole real deep trying to wrap your head around, okay, well, if this is always going to be negative and we're subtracting something, how does it become 0? It just does. The beauty of math. Sometimes stuff just happens. But it does so from negative values, which means as we decrease without bound, our function is also going to decrease without bound. And so there is not a horizontal asymptote going to the left either. Okay? And you might be thinking, well, that was a waste of our time. We didn't find an asymptote, which is why I want to point out his end behavior. So it was useful to know that not only is there not an asymptote, but as we go to the right, the behavior of the function is increasing without bound. And as we move to the left, it's decreasing without bound. So this search for horizontal asymptotes is never without fruit. Okay? The fruit here is we know that it doesn't have an asymptote and it's increasing and then decreasing. Okay? So don't like poo-poo this step. This is very important whether or not we find a horizontal asymptote. And then oblique. We need to worry about obliques. Well, I feel like there's a beach body comment to be made here. Yeah, sure, worry about your obliques, you know, important part of the physique. But I mean more so about oblique asymptotes. How do we know if we need to worry about them? Well, if the degree in your numerator is exactly 1 more than the degree in your denominator, boom, boom, boom. Now we got to worry about the obliques. Better hit those side crunches. Yeah. So obliques will come into play here. And the way that we determine an oblique asymptote is to carry out the implied division by this vinculum here. I don't know if we talked about this year, but talked about that this year, but that's one of my favorite math words. So we're going to pause 10 seconds for station identification. This line here that you just so blithely call the fraction bar. Look out for the students now. This line right here, called a vinculum. Vinculum. I don't know, but it seems like a Latin word. Vinculum? Maybe not. Anyway, the vinculum implies division, and the obliques, we're actually going to do the division and see what results. And what results is going to be the line that acts as our oblique asymptote. That means you can either do synthetic or long division. I'm always going to encourage long division because especially if we have a situation where it's not a linear into a quadratic, like if it's a quadratic into a cubic, you will not be able to use synthetic division. You'll have to use long division. I would say just get in the habit of doing long division because it always works. So long division, what we're going to do is x minus 1 divided into x squared plus 3. So to get x squared, we need an x. X times x is x squared. x times -1 is -x. I always like to do parentheses here, just to be clear, like that this subtraction is going to carry over. The x's go away, sorry, the x squareds go away. That becomes a positive x. Thank you, parentheses. We get x plus 3. So now this becomes a 1. 1 times x is x. 1 times -1 is -1. Subtracting that, and we end up with a positive 4. And so the alternative way we can say f of x is equal to x plus 1, this quotient, plus 4, our remainder, over x minus 1. So we just carried out the division that's implied by this vinculum, and the result is this. And if you remember from 3.7, the reason that this tells us the existence of this oblique asymptote is that as x values get super, super big or super, super small, this guy disappears, okay? And as our x values increase or decrease without bound, our function just approaches x plus 1. It starts to look like x plus 1. So kind of cool. And the result is that y equals x plus 1 is an oblique asymptote. So we've got a vertical, we've got an oblique, and cool. So we're getting somewhere. Where are we? We're at, oh, that was just step 4. Step 4 is a doozy, okay? That was a lot. But step 5, I'm going to kind of put a lot of steps into one and just say derivatives, okay? Because step 5 says compute f prime of x and f double prime of x. Step 6 says determine the critical numbers of f. These are the values in the domain of f for which either f prime of x does not exist or f prime of x equals 0. Apply either the first derivative test or the second derivative test to determine whether a critical number there is a relative maximum value, relative minimum value, or neither. Determine the intervals on which so we're going to just do the derivatives first and second, and then do first and second derivative tests to figure out where are our maxes and mins and where are our potential points of inflection, and then use that information aggregated in a chart, couple that with the work we just did regarding our intercepts, our asymptotes, our symmetry, and come up with a sketch of our graph, okay? So I know this seemed like kind of a never-ending example, but we're getting there. And now the calculus is going to kick in. I guess we did a little bit of calculus already with the asymptotes, but now we're going to really go into overdrive with the calculus. Let's see if I can enable a little more room. Oh, there we go. There we go. Now we're cooking the fire. Cool. Cool, cool, cool. So derivatives. Sure. F prime of x. I guess we'll use quotient rule. Yeah, quotient rule is probably the call. I mean, we could do product rule if we wanted to do x squared plus 3 times x minus 1 to the -1, but that might be more trouble than it's worth. Let's just suck it up and do quotient rule. Okay, so we will do derivative of the top. 2x times the bottom, x minus 1, minus derivative of the bottom, which is 1, times the top, x squared plus 3, all over the denominator squared. Okay, let's do some distribution. 2x squared minus 2x minus x squared minus 3. If we did that right, x minus 1 squared. Doing some simplifying, we get x squared minus 2x minus 3 all over x minus 1 squared. And I'm just going to factor. Oh, beautiful. It does factor into x minus 3 and x plus 1. And this is x minus 1 squared, which tells us that f prime of x equals 0 for x equals 3 and negative 1, and f prime of x dne for x equals 1, which we already kind of knew because there's that vertical asymptote kind of getting in the way of any tangent lines. So that's not a surprise. These will be good information. Okay, second derivative, f Dublet prime. We're going to differentiate, let's differentiate this guy, that form of it. Another room again. Come on, DocCam, do your job. You got one job. Ooh, we got room here? I hope so. Worry about that later. Jump first. Ask questions later. So we're going to again do the, how shall we say, quotient rule. There we go. So the derivative of the numerator, which is going to be 2x minus 2 times the denominator, which is x minus 1 squared, minus the derivative of the denominator, which is going to be 2 times x minus 1. Yes, there is a chain rule, but the derivative of x minus 1 is just x minus 1. Sorry, that's not correct. It's just 1 times the numerator, x squared minus 2x minus 3. Yikes. All divided by x minus 1 to the 4th, because we're squaring that guy. So before we get too flustered by this and start doing all sorts of crazy distribution, we can divide this before we go, okay? There's an x minus 1 to the 4th here, and both of these parts of our difference up here have an x minus 1, at least one of them. So we're going to divide out one of them. So that'll be a cube. That'll go away. That will become just x minus 1 to the 1st. So that does lessen the awfulness of this a bit. Let's do some distribution here. We get 2x squared, negative 2x minus 4x, plus 2. Distribute this negative 2, we get a negative 2x squared plus 4x plus 6. Ooh, this is interesting. Check it out. 2x squared, negative 2x squared, later. Negative 4x, positive 4x, later. Positive 2, positive 6, ocho. Oh, that was slick. So what does this tell us? Well, 8 ain't never going to be 0. So f Dublet prime has no critical points that are equal to 0. So f Dublet prime is never equal to 0. It has the same dne, however, as our function in our first derivative, which makes sense, at x equals 1. Okay. So now we have this information about critical points of our derivatives, and we can go hunting for minimums. What just happened here does indicate that there will be no points of inflection, okay? Because there's no points where it's zero, and furthermore, the place where it doesn't exist that could technically be a point of inflection, well, there's no tangent line at that point, which is a condition of a point of inflection, is the existence of a tangent line. Clearly there is no, well, I shouldn't say that. We will see. We will see. But our hunch is that there is not. Okay. So what we're going to do then is, as we've done many times before, we're going to aggregate this information about our derivatives in a chart to make some conclusions about when are we increasing, decreasing, and then use the first and second derivative test to determine which of these critical points correspond to points of interest on our graph, either because they are a extremum or a point of inflection. So we'll fill out a little chart here. We'll have f of x. We'll have f prime of x. And we are actually going to write out what f prime of x is just to help us. X minus 3, x plus 1 over x minus 1 squared. And then f doublet prime is 8 over x minus 1 cubed. And then we'll have a conclusion column. Let's see if we can make some sense of how this thing is behaving. So the intervals we're going to look at, we're going to go from negative infinity to, negative infinity, wow, let's just start this over. Negative infinity, thank you, to negative 1, the first critical point of our first derivative. We're then going to see what happens at negative 1. We're then going to go from negative 1 to positive 1, because that's a critical point on the first and second derivative, because they don't exist there. Then we're going to go from, or at 1. Then we're going to go from 1 to 3, which is our next critical point of our first derivative. And then we're going to see what happens from 3 to positive infinity. Cool, 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 cool. Okay, so from negative infinity to negative 1. I don't know, let's just 0. Plug in a 0 here. Negative, positive, negative. That's positive. So we have a negative first derivative. Cool. Cool, cool, cool. Our second derivative, we plug in a 0, will give us a negative number. Let me make sure I have the correct first derivative. Yeah. Okay. Which tells us that from, and that's not how this thing behaves. What am I missing here? What am I missing? What did I do wrong? Oh, 0 is not in the interval. That's where I did wrong. Let's try like negative 2. Negative 2 for x gives us a negative here, which is a positive. Okay, there we go. It's a positive. Here we still get the negative. Phew. That was close. What does this tell us? Positive first derivative tells us f increasing. Negative second derivative tells us concave down. Cool, cool, cool. At negative 1, that's when we have our first 0 here. And we could go immediately to the second derivative test here. We plug in a negative 1 to our second derivative. Negative 1 minus 1 is negative 2. you cube that, you still get a negative number, negative 8 to be exact. And so this turns into a negative. If we are concave down at a critical point of our first derivative, that means we have a maximum. Which will be confirmed in a moment when we determine to the right of this point that our first derivative is going to change sign, which will tell us that we've gone from increasing to decreasing with that horizontal tangent in between also confirms the max. So now is where we plug in 0, negative times positive. It's negative. That denominator is always going to be positive. That is a negative first derivative. And so the first derivative test also confirms the existence of this maximum. And here we are negative again, so we're still concave down. Now f is decreasing and concave down. So no change in concavity. Okay. I also think it would probably be worthwhile for us to actually figure out what this point is, what this maximum point is. So plugging in -1 to f of x, -1, that's 1 plus 3, which is like 4. -1 minus 1 is like -2. So 4 divided by -2. Our function value here is -2. So our maximum is at -1, 2. I don't know how you want to mark that off. So max, let's say max at -1, -2. And that'll be one of the points that we plot. Cool. Okay, so then at 1 is where everything kind of blows up because of our asymptote. So we're going to have a DNE for everything. DNE, DNE, DNE. Oh, pardon. Okay. And then we jump into that next interval, and let's see what happens to our derivatives. If we plug in a 2 here, to our first derivative, we get negative, positive. Okay, negative times positive is a negative. We have a negative first derivative. Over here, this turns into a positive second derivative. So f is decreasing. And we are concave up. So you're probably thinking, oh, we switched concavity. Okay. But as we'll see in a minute when we plot this, that does not correspond to the point of inflection because there's nothing happening there. At x equals 1 is just a vertical asymptote. There's clearly not a tangent line there. And so there is no smooth change in concavity. It's going to be like a hyperbolic situation where it's like, so yeah, it changes concavity, but there's no smooth transition, no point of inflection. Okay, at 3 is another 0 of our first derivative. Going straight to the second derivative if we want. Plugging in a 3 to the second derivative gives you a positive number, meaning we are concave up, meaning we have a minimum, which will once again be confirmed as soon as we plug in a value bigger than 3 to our first derivative and see that it's a positive value. The first derivative test then says, oh, we went from decreasing to increasing, the horizontal tangent in between, or even a non-existent tangent in between. That means we've got a minimum. Where exactly that minimum is can be found by plugging in 3 to f. F was x squared plus 3, so 3 squared is 9, plus 3 is 12. 3 minus 1 is 2. 12 divided by 2 is 6. So minimum at 3, 6. And then our second derivative is still positive here, so we are increasing and concave up for the rest of time. Okay, so now I think we've ticked all the boxes, and we're gonna go plot this thing because This example has gone on long enough if you ask me. You didn't ask me because I'm sitting in my kitchen by myself, but not my kitchen, my dining room. It's all kind of the same, small house. Okay, so let's make, what should our axes be? We know we're gonna need to go up to 3, 6. Let's see what the book does for their axes. Yeah, sure. So let's go like boom. I'm not doing any other examples, so we can make this kind of as expansive as we choose. There's a good SAT word for you, expansive. I guess you don't take the SAT anymore because nothing makes sense anymore. Okay, so 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. And we'll go like 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3, 4, 5, 7. We took all this time to find all this stuff out. We might as well be as neat and orderly as we can with our graphs, okay? So yeah, let's just start tossing stuff in. Let's go down the line. The first thing we found out was our intercepts. We had a y-intercept at 0, 3. So let's put that in. Let's go like, I'm gonna go green for the graph because that just alliterates in my head. 0, -3. We didn't have an x-intercept. And then we did some asymptotes. We had a vertical asymptote at x = 1. We use red for asymptotes because that just feels like a power color. Hey, don't cross this line. Okay. Cool. And then we had an oblique asymptote at x + 1. Let me double check on that just because that would be sad. Yes, x + 1. So like this guy. Cool. All right. Okay. So now you guys see what's going to happen here. Like we're kind of going to be like a zoop, zoop. But how exactly does that droop happen? Well, we know that there is from the left, we're kind of going to be increasing, and then we're going to hit -1, -2, -1, -2. And then things take a turn and we plunge down with this vertical asymptote. And then we pick things up on the other side and we're decreasing after between 1 and 3. We're decreasing until we hit 3, 6. That's our minimum. And then we turn the corner and increase approaching that line. So I'm actually going to extend this a little bit. Just a little bit. Okay. So let's kind of go left to right here. We're going to be increasing, and we need to also kind of, so let me extend this too. The oblique asymptote, we're kind of going to be, not kind of, we are going to be approaching this line as x gets really, really small and x gets really, really big. So our curve should reflect that. So it's not like, we're not just going to be like, oh yeah, no. We're going to like really make this tight on this asymptote, and it's only going to peel off at the end to hit that maximum. Okay, so it's almost going to be like a straight line. And then it sort of peels off, makes this turn at our maximum, and then dives down towards that vertical asymptote. And then up here, same story, or similar story. We're coming from this very vertical asymptote. Hitting this minimum. And it's not just like a parabola. Like it doesn't just, it's going to really kind of like magnetize towards this oblique asymptote. And that is the picture of our curve. Pretty stinking cool. Power of calculus. Yeah, so those are kind of the key points that you're going to have to go through as you navigate the exercises. I have it right here. Let me just tell you what those exercises are. It's only 6 problems, but you're probably like, not a lot of work. So 6 problems, but I do want to see this depth and meticulousness on all your problems, okay? So the 6 problems you're going to do for 3.8, be on page 282 to 283. And they're going to be numbers 1, 4, and 7, 17, 20, and 29. Okay. So again, showing careful work, making sure you go through all those steps, checking for all those things. And yeah. So what's left then of this chapter is 3.9, which is kind of a 3.2 type section where a lot of word problems, a lot of ins and outs and what have yous. And then 3.10 is something called Newton's method, which is kind of cool. And so the goal is to finish that out and then start preparing for the final, which will be a comprehensive final, but most heavily weighted towards chapter 3 since we will not be taking chapter 3 test. Okay, but 3.8 sort of wraps up all of the graphing stuff related to the derivatives. And then 3.9 we'll see this return to the 3.2 type questions of optimizing problems or optimizing situations with our derivative. And then 3.10 is sort of a different flavor altogether. And then we'll be done with this chapter. So the end is in sight. All right, stop.